This is where you expect to find the organic chemist, in the lab, doing an experiment. The reaction I was carrying out here was a simple oxidation. I dripped in benzyl alcohol from the dropping funnel into a hot stirred mixture of potassium dichromate in water. In the flask, we do not have the reaction product. We have a reaction mixture. As well as the product, it may contain unreacted starting material, the inorganic reagents which were used in the reaction, and the solvent. So how does the organic chemist set about separating the product from the reaction mixture? Here we have an identical reaction mixture, only this one has been allowed to go cold. The mixture contains both organics and inorganics, and the first thing we do is to pour it into a separating funnel. We work on the principle that like dissolves like, and so we begin by diluting the mixture with water. That takes care of the inorganics. Now for the organics. We add an organic solvent, toluene. The two are then very vigorously shaken together. The inorganics dissolve in the aqueous layer, and the organics, including our product, dissolve in the organic layer. You'll see that the heavier aqueous layer sinks to the bottom as the toluene floats to the top. The bottom layer can then be run off. And the organic layer, now containing our product, has only to be dried and evaporated to give us a crude sample of benzoic acid. This is a much more complicated reaction. No inorganics are involved here, just organic reagents and a solvent. After standing over the weekend, the reaction mixture looks like this. It's dark and tarry, suggesting that we have a mixture of compounds here. How do we set about separating the compounds from such a complex mixture? First of all, we have to find out what there is in the mixture, and for this we use thin layer chromatography. I've dissolved up some of the tar in a volatile solvent, and using this miniature pipette, I apply spots of solution to the surface of the plate. The solvent soon evaporates, and the plate is placed gently in the chromatography tank. The solvent in the tank rises up past these spots on the plate We can see this more clearly using time-lapse photography. Polar compounds in the mixture are held most strongly on the surface of the silica gel. So it's the least polar compounds that travel furthest up the plate. We might even need to change the solvent to get the most polar compounds to move. A TLC plate takes about half an hour to develop. TLC is a very good analytical technique. It tells us what's there, and in some cases, a quantitative estimate can be made. But there's one important snag. TLC uses at most a few milligrams of material. What if we need to separate compounds on a larger scale than this? For this, we need column chromatography. The principle is exactly the same, but it's not capillary action, but gravity this time, which causes the solvent to flow through the column. The column is packed with a slurry of alumina, which is poured in and allowed to settle. The solution from the reaction mixture is applied to the top of the column and is run in and absorbed on the top layers of the column by opening the tap. More of the first solvent is now added to run the mixture through the column. We can see this better if we speed up the action. Bands develop and move down the column, and eventually they're eluted from the bottom. The solvent polarity is gradually increased to elute the more polar substances. The column is now exhausted. This is the last fraction. And you can see we have quite an impressive array of fractions here. But has the column done its job? Do we have single substances in each of these fractions? Well, one way to tell would be to see whether compounds will separate on TLC. This mini plate is just the same as the larger plates we were using. We've done that for all the fractions, and you can see the results on the mini plates. Fractions where the plates show a single spot can be taken away and evaporated to yield the product. Those showing more than one spot, the mixtures, are returned for further chromatography. Column chromatography is an immensely powerful technique, and although it can be automated for the collection of fractions, the simple procedure that we used here is perfectly adequate. Further purification of these evaporated fractions yields the beautiful crystals we have here. We've come a long way from our original tar. This is glowing sugar cane, the source of sugar, perhaps the most familiar organic compound. The problem for the sugar industry, too, is a problem of separation, for the sugar is all mixed up with unwanted woody stems. Burning off the unwanted foliage is the first step in the extraction and purification of sugar. Then it's harvested. And in sugar mills, it's ground up and leached with hot water. It's from this mesh that the first raw sugar crystals form. But it's not pure yet. It's in this brown, raw state that it's shipped to sugar refineries all over the world. Here it's purified a second time by recrystallization from a saturated solution. these pure white sugar crystals are dried, and the familiar white sugar is packaged for sale. Allowing crystals to form as a hot solution cools is the way of purifying organic solids in the lab too. Recrystallization is the lab equivalent of refining. Remember that first reaction? We've evaporated the organic solvent and we have a crude sample here of benzoic acid. It's not yet pure, it needs to be recrystallized. We recrystallize organic solids by dissolving them in the minimum quantity of a hot solvent using a conical flask. There are good reasons for using a conical flask, not least of which is that it stands nicely on the hot plate. When all the solid has dissolved, we filter the solution using a cone filter with the stem removed. This is so that the crystals don't form in the stem and clog it. And we use a fluted filter paper. The large surface area allows very fast filtration. The crystals have all dissolved in this solution of benzoic acid. Filtering at this stage allows us to get rid of fluff and dust and undissolved solid. The crystals form as the solution cools. When the solution has reached room temperature and crystallization is complete, we must filter off the crystals, not this time using a cone filter, but using a flat bed filter and a Buchner funnel and suction. The reason we don't use a cone filter is that crystals in a cone filter are still soggy with solution, whereas the crystals out of a Buchner funnel look like this. Now we have something that deserves to be called a pure organic compound. Let's see why it is that recrystallization brings about purification. The line on this graph shows how the amount of solid that dissolves in a fixed amount of solvent increases as the solvent temperature is increased. The columns represent an impure solid in which the required material is contaminated with an impurity. At room temperature, some of the solid dissolves in the solvent. Heat up the solution, and more of both compound and impurity dissolve, until, at the boiling temperature of the solvent, all the solid has dissolved. We now cool down the solution. Some of the solid can no longer stay in solution at the lower temperature, and so crystallizes out. Most of this is the compound we want. When room temperature is reached again, some of the solid is left in solution, but most of it has crystallized out. The precipitated solid we filter off now contains much less of the impurity than the crude sample, and this contamination is removed in a second recrystallization. Well, after all that hard work in the lab, how about a drink? So far, we've only talked about organic solids. But here we have a familiar organic liquid, the aristocrat of organic liquids, some would say. To get from the raw spirit to this state, we need to purify it. Particularly, we have to separate from it that most serious contaminant of organic liquids, water. Clearly, a separating funnel is no good here. We need a different technique, distillation. Malt whiskey is made from a single natural material, sprouting barley or malt, as the distillers call it. After milling, the malt is mixed with hot water in this tun to make the thin porridge-like mash. The liquor which drains off the mash, the sweet wort, contains mainly sugar, which on fermentation will yield the alcohol. After about 48 hours, the wash is drained from the fermentation tuns, ready for distillation. The first stage of distillation takes place here in the wash still. The fermented liquor runs into the still where it is heated to a certain temperature. The vapors of those compounds with the lower boiling temperatures rise into the neck of the still and drain outside into the picturesquely named worm. This is simply a coil cooled in a tub of water through which the hot vapor descends. It's easier to see when the water has been drained away. The vapors condense as the tube coils worm-like, round and round, down and down to the bottom, where it is led back into the building, to the safe. Like all good chemical processes, we have to check it to see how effective it's been. And so we're able to take continuous samples, checking them for specific gravity and for temperature. This is the critical part. By checking on the specific gravity and the temperature, the distiller is able to adjust the flow rate and therefore the quality of the distillate. Once the distillate has passed through here, it is returned to a second still where it is distilled yet again. And the product of the low wines, the feints, come back into the factory here. The feints are redistilled and the product, the spirit, comes back here. At each stage, the product is monitored by checking the specific gravity and the temperature. So here we have the real stuff, the pure spirit, 120 proof. But how pure is it? This GLC trace of the Rosebank whiskey shows that the output from the spirit still, the third distillation, is almost pure spirit, ethanol, but that small amounts of other organic liquids are also present. How do we carry out a simple distillation in the laboratory? Well, this model of the Rosebank still shows many of the features. We have a distillation vessel, a source of heat, which at Rosebank is steam, and the takeoff leads the vapors into the condensing system and to the outlet where the condensed liquid can be collected. The lab apparatus is very similar. We have a distillation flask, a condenser, and a receiver. The differences are that the lab apparatus has to be more versatile to handle a wider range of boiling liquids. We have to be able to take our apparatus apart for easy cleaning. We use anti-bumping granules to ensure smooth boiling. And quality control is measured by the temperature of the vapor in equilibrium with the liquid at the thermometer bulb. Again, we have to ask the question, how is it that distillation brings about purification? The theory of purification by distillation is more complex than that of purification by recrystallization. Let's take a mixture of equal volumes of two liquids which have different boiling temperatures. We now heat the mixture and distill off about half of it. the distillate is richer in the liquid of lower boiling temperature, and the residue richer in the liquid of higher boiling temperature. If the distillate is redistilled and we again collect about half the mixture, this distillate is mostly the liquid with the lower boiling temperature. It is a fairly pure sample of this liquid, but we have only recovered about half the amount that was present in the original mixture. The combined residues, about 3/4 of the original mixture, though richer in the high boiling liquid, are still very impure. If these combined residues are now redistilled, more of the lower boiling liquid can be obtained. At each successive distillation, the residues become richer and richer in the higher boiling liquid. We've seen how the whiskey distiller doesn't want his distillate to be too pure. It's the trace impurities that give whiskey its distinctive and, of course, its expensive flavour. But the lab chemist does want pure distillates. What can he do to improve the quality of his distillate? Well, one thing would be to do the distillation over and over again. This would be very tedious. Unfortunately, there's a better technique: the fractionating column. This distillation flask contains a mixture of organic liquids, and the fractionating column is packed with glass beads. As the vapours ascend, they condense and trickle back, but further hot vapour rising up the column causes them to be redistilled. This goes on several times until, at the top of the column, vapour from the pure, low boiling fraction distills over, is condensed and collected. This is a rather crude column, such as might be used in a teaching lab. In the research lab, where the separations become more difficult, more sophisticated apparatus must be used. The people with the biggest problems in trying to separate organic liquids with close boiling temperatures are the oil chemists, and they've come up with the biggest solutions. The fractionating columns down there on the oil refinery work in exactly the same way as the fractionating columns in the lab. They're just bigger, and they do their job better. That's all.